Everyone, my name is Arian and I am a 13-year-old that is super passionate about brain-computer interfaces. And today I have something really special for you guys because I'm going to be covering one of the projects that I've been working on for the past few weeks. And this is in essence replicating some previous research that has tried to use deep learning and different types of machine learning models to correctly classify between whether somebody is blinking or not based solely on their brain signals. And you may be thinking, this isn't the most eventful thing and this is nothing new. However, most people, when they're classifying blinks, do not use machine learning and can lose a lot of accuracy on stuff like basic classification. And the thing about why blinking is so important is that in the field of brain-computer interfaces, you would know that whenever somebody blinks, it can give off roughly 10 times as much voltage in a neural signal as compared to regular baseline readings. And if we can detect blinks properly, we can potentially remove these blinks properly as well to normalize data, which makes it super important for applications anywhere really. So how about I show you more into my project? So to start off, I looked into finding a proper data set for where we could find many people's EEG signals that were blinking and whether they weren't blinking. And a great place to find this, just a great place to find data sets in general, is known as the University of California, Irvine, or UCI Machine Learning Repository. And what I have open for you here is the data set that I use in my project. So what this dataset has is the reading of many different people that have roughly 100 seconds of EEG readings, or electroencephalogram readings. And each reading is matched up with a certain state where 1 means your eyes are closed and 0 means your eyes are open. And just a quick download of the data would show that this data set is huge, and this is the amazing thing about machine learning. We can leverage the power of computers to correctly identify and process data to do useful things for us, which humans cannot do on their own using hard coding. So once I got this data, I used an amazing toolkit known as Microsoft Azure Machine Learning Studio. And the great thing is that this is on a free trial, and I have currently the power of any huge company that is working on any brain-computer interface project in the world. So this provides a lot of leverage. So let me provide you some insight as to what I have done. So when I go into this project, you can see that it's just a drag and drop method of creating deep learning networks. And the amazing part of this is that I did not have to write a single line of code to get analysis that was superior to almost any other toolkit out there, which is amazing. And when I'm deploying this model, I can potentially make it much more feasible to use and much more easy to deploy than any other production based company out there. So what I'm going to do is just going to give you a basic rundown of the model and step-by-step framework of how it runs. So to start off, every machine learning model needs some sort of database, and the database that I described earlier is exactly what we see here in our EEG data. So just to give you a quick visualization, I will just open up this, and as you can see, the data set is huge. And just for reference, this data was gathered by a completely open source neural headset known as a emotive headset, which looks something like this. It has 14 channels or 14 different electrodes that are placed non-invasively on your head to record signals coming from clusters of neurons. It's really a simple process, but the implications are absolutely huge in this field. Just recently, a quadriplegic was recorded in terms of brain signals, and when their muscles were electrically stimulated, they could move their muscles again. And one of the main applications of recording blinks in brain-computer interfaces is that, as I already said, once you can define and record specific blinks, you can remove them to normalize your data better and to, in an essence, just remove noise, which is really important in something as sensitive as converting thoughts into actions for fields such as prosthetics as well. So back to our data. You can see that there's 14 different channels. Each patient has an ID, meaning that there are thousands of patients, right? But each ID is linked to a certain amount of data, and this is recorded from each specific electrode, which I chose to label A, B, C, D, E, F, all the way to N. And this is just an optional set, but when deploying the model, this really helps. And as well, there's a state, where 0 means your eyes are open, and 1 again means your eyes are closed. So if we were to scroll down, you would see that if you kept on scrolling down, that your eyes would be closed in certain instances where the state is 1. So after that, I sort of selected specific areas of this data set for use. And one of the main things that you have to see in this is that you have to remove certain columns of your data, because some columns are clearly indicative of your answer. For example, in a MATLAB model that was being used previously for this data set, I achieved accuracies of up to 99.4%, and I was wondering what was wrong. And what ended up being wrong was that I included the patient's ID number in this data set, and the fact was that the data set was not shuffled properly, meaning that there were huge clusters of zeros and ones inside of our model that were not randomized, meaning that our model, instead of learning to use the electroencephalogram data to predict this, it was using ID specifically. And what I've done is just excluded ID in this case, which is anyways not a predictor that is going to be used in production models. After this, once I have chosen a data set and my data has been cleared of any unnecessary columns, I can clean any missing data. And although we did not have missing data in this case, it is a really good practice to be doing this, because in models in general, you can have missing data, and clearing it up can really improve the accuracy of your machine learning model. Next up, what we did is we split the data into training and testing splits. In essence, it's just two different folds of your data. Each fold is used for its own purpose. The larger portion is used to train the model, and a smaller portion is used to cross-validate and score the model. And after that, what I did is I used a specific type of model called a two-class boosted decision tree. And of course, the choice of a model is most of the times arbitrary. However, some models can definitely perform better than others. And during the development of this project, as I was replicating research suggested that boosted decision trees, a specific type of model that relies on going through, in essence, many different if-then statements with their own thresholds to classify a state, research proved that it was statistically and both proven physically, it was the best model for this type of application. And in my experiment, this was further reinforced. So this model was trained, and it achieved amazing accuracy of, here, 1 second. Just for context, I would like to show you how a model predicts. The model, where the state was 0 and the scored labels were 0, the probability was scored at 0.00034, which statistically is 0. And in a case of 1, the scored probability was 0.09999. This confidence is amazing for networks of this class. And for something such as two-class boosted decision trees, which is a relatively simple model that required no code, the performance of this model is exceptional. And after this, the model was evaluated, and the results were exceptional. The accuracy of this model increased drastically, and has a very low false positive and false negative rate. The accuracy of this model, 0.944, or in other words, 94.4%. This research that I've replicated and I have done completely without a line of code has an accuracy greater than most production models currently in use. And that is the power of brain-computer interfaces. In the future, I'll be deploying this model for public use where you can input your own 14 channels of electrical signals into this, and you can figure out if you've been blinking or not. And I think that's amazing because in the future, brain-computer interfaces are going to need this technology to grow and fully expand because you need to normalize your data in a way that is very sustainable, very efficient, as well as very, very accurate. And to date, this is the most accurate model that has ever been used for this data set. Now, just the implications of this are potentially amazing because now if we can diagnose diseases with brain-computer interfaces, and we can classify blinks, and we can already just make quadriplegics move with brain-computer interfaces. Imagine what's next. And just as reference, look at what I've done in 2 weeks with such a regular and widely available commercial toolkit such as Microsoft Azure to create such a model. Imagine what companies can do with the power that they have in millions of dollars of funding. And this is going to be an amazing future. And this is the future that I'm trying to build. And I hope you look forward to it too. The future of brain-computer interfaces. Thank you.